welcome to lecture 2 of the course on computational geometry. I would like to reiterate a couple of things that got left out. So, for recap, I left you off essentially at this point, that I was defining something called this art gallery problem, right, where this is a huge hall, okay, and there are rooms in this hall. So, I only marked out the boundary of the hall, and there are essentially paintings on the wall, which must be looked after and monitored by guards posted, so that they cannot be stolen, right. And we would like to post as the minimum number of guards, such that every painting must be visible to at least one guard. Okay. So, that is the art gallery problem. So, how does one go about solving this problem? How does one even attack this problem? So, let me take a simple case. So, this particular hall has these the turned corners, and so there is not, it is not really the shape. The shape is not very even. It has these turns and twists, which actually makes life harder in when we want to decide where we want to keep guards. Okay. Now, instead of this, okay, if we had a situation where the hall looked like this, just let us say a rectangular hall, would the problem be any easier? Where should I post the a guard or the guards, so that every painting is visible to at least one guard. So, these are the paintings. You can, for simplicity, again assume that the wall is full of paintings. Okay. So, in other words, what I am saying is that every point in the boundary, of course, the interior boundary, should be visible to at least one guard. And the guard has circular vision. It is like a snail, it can sort of see all around. So, for this particular instance, what is the solution? I can actually anywhere, right. In fact, I can choose this point or this point or this point. It really does not make any difference, because why? You look at any point on the boundary, okay, choose any point on the boundary, okay, and I can join this point on the boundary with the location of the guard, and this straight line segment is not going to intersect any of the walls. Okay. So, that is what makes the problem rather simple and straightforward. Right. So, what this shows is that there are certainly situations where the problem is really simple, and of course, you need at least one guard. Okay. So, this will take care of it. Okay. So, this is about the case where it is a rectangle. Even if it were a square, it would probably be the same, right. Or what about if it were a disk, if it was something like this, even then it seems okay. All right. Okay. So, let us try to make it a little bit more complicated. So, how about this? Well, you are giving me an answer, but the first question is that why do you think one guard is not sufficient?
Anywhere there is a, if the object is convex, then you can put anywhere in that, and that will be. The problem happens when there is some concave things like that.
So, there is a cusp, essentially there is a cusp. So, I have not formally defined convexity. If you are familiar with convexity, you know that is a good answer, or at least it is in the right direction. But then it appears to us that, you know, if I put a guard, certainly if I put a guard here, I can argue that, you know, this portion is not visible to the guard. You know, this guard certainly can't see anything here, and vice versa. But, you know, if I move this guard, you know, if I move this guard and try to bring him somewhere here, okay, perhaps everything is visible. So it's not just that, you know, I am constrained, that I am looking for a solution where I should be able to put the guard anywhere. I also have, I can choose the location of the guard. So if you want to argue somehow that one guard is not adequate, okay, we have to argue that no location, there is no location in this hall where everything is visible. Okay. So can you argue about that?
You can show that these 2 points cannot be visible from a single location. You can choose such points and show that if they are paintings at these points, there cannot be a single location from where.
Okay, all right. That's a good attempt. So so what you're saying is that, you know, suppose I have a painting here and a painting here, okay, and then I want to somehow find out, you know, if there is a location from which both these paintings are visible, and will be hard pressed to find that. In fact, you can probably argue that for, so suppose this is the corner, okay, so somehow since light travels in straight lines, okay, this painting can be visible only if the guard is in this portion, right. You know, the moment I move the guard here, you know, the straight line is basically will be such that it can never intersect the painting without intersecting the walls, right. Okay, so that's essentially the idea about, you know, how one can argue that, you know, more than one guard may be necessary. The other thing is to somehow argue that whatever, do you think 2 guards are sufficient in this case? Do you think you will require more than 2 guards? We have argued that we need more than 1 guard, but are 2 guards sufficient? Okay. So I guess how would you argue about that? So certainly if I am constrained to put a guard in this rectangular, this shaded region, okay, I am constrained to have some guard in this shaded region too, right, because again this painting must be, or this portion of the wall should be visible to that guard. So how do I now argue that everything else is visible? Well, if I put a guard, you know, anywhere here, okay, from our previous argument, okay, this entire rectangle should be visible from here, okay. So now you only have to argue about the left shaded portion and the middle. Yeah. So so this, if I post a guard here, even this guard can actually view everything, yeah, within this rectangle, right. So if you look at this rectangle, everything is visible. So that's how you can argue that, you know, everything should be visible to 2 guards. So 2 guards are sufficient, okay. So in this case, what we are saying that 2 guards are necessary and sufficient. It's a fairly strong statement. All right. So this is by visual inspection. Okay. The algorithmic problem is that I am given the description of this hall, okay, and the hall can be of any shape, and somehow we are supposed to, let us say, algorithmically determine, you know, what is the minimum number of guards that we require, you know, and that's a challenging problem. Okay. Let's try some more examples. So we are worried about someone said something about convex. Okay. So convex, let me come to that. I'll come to the definition just a little later, maybe today itself, but even prior to that, let's try something again which has a cusp. Okay. So let's try another room. Okay. Let me relax again the condition that the halls, the walls must be, you know, parallel to the coordinate axis. You know, let's relax that condition and allow for what is called essentially a simple polygon. Okay. So, I could have a situation like this, right. So, this is a more modern, let us say modern architecture hall, so you are not constrained to build everything in rectilinear fashion. So, this has again that problem that it has these cusps, right. So, essentially if I put some guard at this location, this region is not going to be visible to this guard. But then how many guards do you require for this this figure or this hall? Okay. So, by inspection it appears that if instead of putting this guy in a corner, if I somehow move this guard to come towards the center, okay, seemingly everything should be visible. And why is that? We can argue that again. So, I can complete this, let us say this triangle and complete this triangle. Okay. So, this left triangle, this is visible from any point within the triangle. So, L is visible. Similarly, R is visible from any point within the triangle, and this lies in the intersection of the two triangles. So, the entire polygon, interior of the polygon is visible. All right. So, just to make sure that we have our definitions consistent. So, let me define the notion of a simple polygon. It is a closed area on the plane that has a boundary comprised of straight line segments that do not intersect. Okay. In other words, it is a closed figure. So, I should be able to draw it without lifting my pen. Okay. So, in other words, I could draw. Okay. So, this is also a closed figure, except that it has self intersections. The the boundaries intersect. Whereas, if I have something like this, where there is no self intersection. So, this is a legitimate simple polygon. Okay. So, it has a well defined interior, okay, and it has a boundary. Okay. Sometimes I will call it BD. So, this is interior, okay, and this is the exterior. Right. So, simple polygon is also sometimes called, in a more general sense, sometimes people refer to it as a Jordan curve. So, Jordan curve is a property that it actually partitions the plane into three parts, namely the interior, the boundary and the exterior. Okay, Jordan curve can actually need not be straight line segments, but any kind of curve. Okay. So, this particular simple polygon that we just investigated, okay, although it has these cusps, so it has these bends, which go inside, okay, as opposed to something that looks fat like this, which is what essentially is is a convex figure. Even here there is a solution with one guard. Okay. So, these kind of polygons, although they are not what we call convex, okay, they are called star shaped polygons. And of course, we have the notion of convex polygon. Okay. So, the convex polygon in short is something like this. If I can draw, so take any 2 points in the interior, okay, if the segment joining them does not intersect the boundary, then it is convex. Okay. So, this is the quantification is that for all pairs of points x 1 x 2 or let us say p 1 p 2 sorry. Right. So, all points p 1 p 2 this should be true, right. And therefore, something like a figure like this, if I take these 2 points, okay, and I draw a segment that will intersect the boundary. Of course, there are points which I can join without intersecting the boundary, but if you take a convex polygon like this or even something like this rectangle, take any pair of points, I can always join them so that it never intersects the boundary. Okay. And what is the smallest simple polygon or convex polygon? Triangle, right. So, triangle is the smallest simple polygon, and also it also happens to be convex, right. Okay. So, for convex polygons, we can essentially claim, because of this property, that one guard is adequate, because whichever be the point on the boundary, I can always draw, I can place the guard anywhere, and I can join the guard with that point that does not intersect the boundary, and therefore, it is visible by definition, right. Let us again generalize generalize the problem to what we are looking at. So, we are only looking at every point in the boundary should be visible. Okay. From here, let us say that not only every point in the boundary, every point inside in the interior should be visible. Okay. So, what I am saying that I am extending the problem, the scope of the problem, where I am saying that we want to actually place the guards in a way such that every point in the interior is visible to at least one of the guards. Okay. So, maybe you are not constrained to put the paintings only on the walls, but sometimes we have these exhibits on the floor somewhere. So, every point should be visible to at least one of the guards. No. So, there are some examples where it is not so. Okay. So, one has to work hard to create those examples, but there are actually examples where you can all the points in the boundary is visible, but not all points in the interior is visible. Okay. So, I will come to that. Maybe I will not actually even take it up in this course, in this lecture. So, let us investigate more. So, what about an arbitrary? So, we have seen that for a star shaped polygon, okay, a star shaped polygon, okay, what is a star shaped polygon? It is defined the convex polygon. I have not defined a star shaped polygon. So, star shaped polygon basically has a property that from at least one point everything is visible. Well, everything in the interior is visible. Okay. So, the star shaped polygon need not be necessarily convex, as we have shown in this example, okay. But there is here in fact it is not just one point, this entire region is such that if you place a point in this shaded region, anywhere in the shaded region, everything inside the polygon is visible. Okay. And sometimes this is also known as the kernel of the polygon. So, the star shaped polygon has a non-trivial kernel. So, from well, this is one of the definitions. So, it has a non-trivial kernel. There may be other alternative definitions equivalent.
The point from where all the
yes. Okay. So, we know about star shaped polygon, we know about convex polygons. In both cases, actually one guard suffice. Okay. We have seen some cases like this one where one guard does not suffice. Okay. And in general, as I said, our goal is to the goal is to given any arbitrary let us say now we are dealing with polygons, any arbitrary simple polygon, find, let us say algorithmically the minimum of guards. Okay. In other words, we could have a really crooked polygon something like simple polygons can be actually quite complex. As long as they don't intersect, these are the games that you used to play as children, right? You have to draw things without intersecting. So, this is a simple polygon, it has a well defined interior. Is it bad enough? Yeah, right. So, now I can challenge you that I do not think in the next 2 minutes anyone can actually tell me what is the minimum number of cards required here. Okay. And of course, we can make it much worse, So, you may have to struggle for not only 5 minutes or 10 minutes, perhaps 5 hours. In fact, the problem gets sorted very quickly. Okay. And the answer is that, well, the pessimistic answer is that this problem is an NP hard problem. Okay. So, for people who have done a course in algorithm, they should know what this term means, which means that if I give you a simple polygon, an arbitrary simple polygon with n vertices, there is no known polynomial time algorithm that can find out the minimum number of guards, okay, for an arbitrary polygon. Of course, for some special cases we can. Okay. So, that is a pessimistic answer. So, what do we do at this point? Well, not much. I mean, algorithmically not much, except that people who believe in approximations, we may still be able to do something, and I will say a few words about that too. But before that, let us try to tackle at least some kind of combinatorial aspect of this problem. Okay. That so, here is an alternate question, which is not quite an algorithmic question, but more of a combinatorial question. Okay. For a simple polygon with n vertices. Okay, by the way, so how many edges does a simple polygon have? Same, right? N and n, n vertices, n edges. And what would be a good representation of a simple polygon? I mean, after all, if you have to solve something algorithmically, you have to represent it inside using some kind of data structure, right? Yeah, right. Just a list, but an ordered list. We do not want to lose the information about the adjacency, right? We should know that after this point, it is this point and this point. So, it is not just a set of points, but the set of points are actually the corner points are connected in a certain way, and that defines that particular simple polygon, right. So, it's a circular list essentially, or whatever, an array or whatever is the natural representation for a simple polygon. So, for a simple polygon with n vertices, what can we say about number of guards required in the worst case, maximum number of guards required in the worst case. And it will be great if these two numbers actually match, so that we can come up with some answer, okay, where we can establish that the answer to number 1 is the same as number 2. Right? Otherwise, our estimates may not be a good estimate. Right? So, one clear answer. Let us look at number 2 first. Okay. What is the maximum number of guards required for a simple polygon with n vertices? Okay. So, why are you saying it should be n? Okay. So, if you have a guard posted at every vertex, okay, well, the edges, the boundary is certainly visible. So, can you argue about why the interior should be visible? It certainly makes sure, because if you have a point on every edge, that entire edge should be visible, which means the union of the edges is visible. So, n guards certainly suffice when we are talking about boundary visibility, but if you are talking about interior visibility, This may not be all that obvious, you may have to use some kind of geometric reasoning.
All the boundaries are visible, then the interior is.
What is that result?
Sir, if you take three consecutive cards and make a triangle some sort, you can exclude that part of the.
No, no, but you take three consecutive things. Let us say I take three consecutive things, this, okay. This triangle is actually even exterior, right? Or you could have a situation where yeah, essentially, so you don't even have a triangle. But you have hit upon some good idea and intuition, that is, if we can somehow say that we can partition a simple polygon into triangles, then we are done. Do you agree with that? Right? Because we are that triangle must have at least one external edge, or not necessarily by that. No? Yes? No? Not necessary. Okay. Let us try this. Right? Sorry, just one moment. This is not a good example. Just one moment. Right? Okay. And I can have a triangle. Well, no, sorry, this one, not this one. Okay. But then it must at least have a corner point, right? And if we place the guards on a corner point, so what I am saying is that it is not true that a triangulation always has the property that one of the edges is the edge of the polygon. So, this triangle does not share any edge with the polygon. But on the other hand, if you place a guard in any of the vertices, of course, the entire triangle is visible. So, if we can somehow establish that we can so observation 1, if we can triangulate a simple polygon, then n guards posted at vertices suffice, right. This should be, this is the lesson that we have. There was some question about what was that, about maximum? So, whatever be the shape of the polygon, we should be able to prove that I will never require. So, this n guard is not dependent on the shape of the polygon, right. Whatever be the polygon, if I can triangulate that polygon, if you can establish this, that a simple polygon can be triangulated, then n guards will suffice whatever be the shape of the polygon. It does not depend on star shaped or convex or whatever. So, that is what I mean by worst case.
But then I can also say that n plus 1 is also the worst case, because I can place n on the corner.
Right. So, that is why I said when we have a solution to this 2 and the solution to the 1, no. So, we want a solution to 2 and solution to 1 which should be matching. That basically means that the bound should be tight. So, I should be, if you say that the answer is n plus 1, then I should be also able to I should be able to demonstrate that in some cases n plus 1 is necessary. So, that is what I meant by we should be able to get matching bounds for 1 and 2, otherwise I can say n square, n cube, some arbitrary number, clearly not, right. That is why we are looking for tight bounds such that 1 and the figure in 1 and 2 should match, okay. That should be our goal, all right. Okay. So, can we try to kind of justify this thing that we can triangulate any simple polygon? Let us first try this. Okay, let us try that. Okay, even before we try that, see the challenge is basically to be dealing with this kind of crooked polygons, right. So, I should be able to demonstrate the following, that if I could draw, for instance, some edge connecting two vertices such that the edge completely lies inside the polygon. suppose I could prove, I could always do that, then I have a solution or I have an answer. I have an inductive answer. Why? Because I know that a triangle is obviously triangulated, and any other simple polygon, I can, if I can draw, this is called a diagonal. Okay. So, if I can draw a diagonal, that is an edge joining 2 points that does not intersect the edge of the simple, any edge of the simple polygon, then I can apply this inductively. It is also a kind of a constructive proof. Right. So, all I need to demonstrate is that I should be able to draw a diagonal of a simple polygon, and then we are done, because now we are dealing with smaller polygons. So, how do we justify that? So, for that let us try this idea. So, consider the so what are we trying to prove? We are trying to prove that we can claim always find So, once it is not a triangle, we should be able to find a diagonal. Right. So, I will do a kind of a proof sketch. So consider the leftmost point of the polygon, which is a vertex, right. So, we have a polygon, some arbitrary polygon, etc., something, okay, and this is what I mean by the leftmost vertex. Let us call it L. Is the leftmost vertex of the polygon. Now, consider the two adjoining vertices that are connecting to the L. Okay, say call them, let us say A, and call them B. Call them A and B respectively. Okay. They are both to the right of L, because this is a leftmost point. Right. Now, if let us draw this diagonal A B. So, in this case, great, works out. Okay. However, that may not always be the case. If we could draw that diagonal, we are done. Okay. But we could also have a situation where we have a situation where something like this, right. So, this is my L, this is my A, this is my B, okay, or let us have something even more general. Sorry. This is my polygon. Okay. So, when I try to draw this diagonal, it is not, this edge is not a diagonal clearly, okay, it intersects the polygon. So, if it intersects, then you pretend do the following, you take this edge A B and translate it to the left towards L. Okay. So, you move this, okay, you move this, okay, at some point, okay, you are beyond which if you move, it will completely lie in the interior of the polygon, right. So, clearly if it is very close to L, it has to be completely interior to the polygon. So, now you see that there must be some last point that it must have touched, okay, and that has to be a vertex. So, if this is a vertex, then this must be completely inside the polygon. So, this must be a diagonal. So, this tells us that for a simple polygon, we can always find a diagonal, and hence we can always triangulate a simple polygon. Right.
One question in the when we consider L and its two adjacent things, can't they be collinear?
Yes, but you can always. So, the question is the following, that I have. Okay, so let me just repeat it. So, here I have taken a situation where there is this L, but suppose I have L1 and L2. That is what you are worried about. Okay. What I am going to do in this situation, this is this L1 L2 is parallel to the y axis, right. So, there is no unique leftmost point, but then what I can do is I can always do a random rotation and I can fix a leftmost point. I can always find a unique leftmost point by orienting the axis, and that does not change anything about the triangulation. Okay. So, many of these so in many situations we will come across these cases where I will just make a reference to that, we can always orient the coordinate axis, and in most problems the solutions will not depend on the orientation of the axis. In some cases they will, okay, but for instance here it does not really depend on the orientation of the axis. Okay. So, now we know that we can triangulate a simple polygon. So, that is good news for us. So, which means that our conjecture that n guards suffice is certainly correct. Question is, can we do anything better? Can we get a bound better than n, square root of n, half n, something like that. So, any guesses? Can it be less than n? Do you think it can be less than n?
We need to find bigger convex hull to fit it. So
Convex hull is something that is
bigger polygon.
quite far from today's lecture. Yes.
So bigger polygons, instead of triangle you use rectangle, so kind of get more vertical.
No. So, when I talk about okay. So, what you are saying is that instead of triangles, if I can partition the polygon into other kinds of convex shapes, maybe I can get a better bond. That is a good idea. That is something that we can follow, but let me work out a different proof, which is a very clever and beautiful proof. So, that is the reason I will discuss it.
But in this case, when you are triangulating, for example, the triangle has two vertices on the boundary, right? You don't need both of them.
Right.
You
So,
actually
something
have
exactly. So, things do appear redundant even in the case of triangulation, right. Why should I have a point at every vertex of every triangle? Okay. Something because the kind of triangles share some common edges and things like that. So, that is the intuition why this bound that we have of n we should be able to improve. Okay. So, that is precisely what I will do. So, so this is what I will use. So, I will make a reference to what I call the coloring of the vertices of a triangle. Okay. So, coloring the vertices of the triangles of a given triangulation of the simple polygon. So, you consider any simple polygon, okay, and I consider triangulation of that. So, this is a possible triangulation of a simple polygon. So, we want to color the vertices of the triangle. So, let us say this is triangle T1, this is T2, this is T3, T4, T5, T6, T7, T8. Okay. So, there are these 8 triangles, and I want to color the vertices of the triangles in such a way that no two vertices sharing an edge should have the same color. That is the usual notion of vertex coloring. Okay. So, in a way such that no two endpoints actually triangle same color. Okay. Now, what do you think is the minimum number of that? I mean, what is the minimum colors that we require for this purpose? So, even if you can't guess, let us assume it is some number. Okay. Let us suppose it is C. So, suppose I require C colors, okay, to color the is the number of colors that we require to achieve this coloring, minimum number of colors that are required to achieve this coloring. All right. So, if this number is C, okay, then what can we do? So, we know that in any given triangle, it must use at least 3 colors, right, because any triangle by this definition you want to color a single triangle, the simple case, I need at least 3 colors, 1, 2, 3, because all these edges, the 2 endpoints of the edges should have distinct colors, right. Now, okay, I am saying C, maybe it is not a good idea to work with C. Let me work with actually. So, let me actually give you the answer. Let me go back and give you the answer. Okay. So, claim it can be done using how many? 3 or 4. I do not know how you got that, but 3 happens to be the right answer. Okay. And you see that 3 is the minimum to even color a single triangle. Right. Now, if you can color this triangulation, or whatever be the triangulation of a simple polygon using 3 colors, okay, it implies that some color is used no more than what? 8 n over 3, actually is even better, n over 3 the floor of that. Some color is not going to be used for more than n over 3 times, right. Now, I claim that if I place a guard, so whatever that color is, suppose I am using red, blue, green, okay. Suppose it happens to be the red color is used no more than n over 3 times. I claim that if I put guards exactly at those corners, the entire polygon is visible. Right. See, every triangle must have 3 colors, and therefore, it must have necessarily one of the vertex with a red color, and therefore, and the entire triangle is visible from the red color. So, if every triangle has a guard posted at the vertex that it has red color, then the entire polygon is visible, the interior of the polygon is visible. Okay. So, this proves that n over, so in fact, let me go back. So, where I posed the problem was, yeah. So, the answer to the second question, we have the answer to the second question, right. Maximum number of guards required in the worst case is n over 3. It would be very nice if you can somehow show that there are actually polygons. Okay. So, the next thing that one would like to establish is that, so can we show that there are simple polygons where n over 3 guards right, then we have a good bound, because this is a tight bound, that there are actually polygons where you require that, and this for today I am leaving it as an exercise for you. No, so you should be able to show it for any n, for any n. Okay. This one?
These, 3 colors are sufficient, the claim is. So, this graph, this planar graph, this graph has
okay. So, other thing that I want you to prove is this claim. So, for today I am leaving you with the exercise that you must prove, somehow try to prove that any triangulation of a simple polygon, those triangles can be colored using 3 colors. Okay. That I have not done the proof here. Think about it, how do you want to prove it? It is not hard. And this one, the other part, that can you show that there are actually simple polygons which will require n over 3 guards. You can't do with less than n over 3 guards. Okay. So, there are 2 things I am leaving an exercise today. So, this one you only have to show, somehow demonstrate, actually show me a figure where n over 3 guards will be necessary, and the shape should be such that about this many guards should be necessary. And the proof of this theorem in this this is called the art gallery theorem, actually the 1 and 2 together, that is known as the art gallery theorem, and it was first a proof was given by Shvatal. But his proof was not this proof. This is much simpler proof. Shvatal's proof was somewhat harder. Okay, this proof is a really cute, beautiful proof. So I could do it in 10 minutes. So this is known as the art gallery theorem. So let me again go back to the algorithmic question. So we have answered some kind of a combinatorial question, that there are polygons for which n over 3 guards are necessary and sufficient. Okay. That is what we have proved. That is the art gallery theorem. There are, for every n, there are polygons for which we require n over 3 guards, and n over 3 guards are sufficient. All right. But the algorithmic question, as I said, is cannot be solved because it is known to be, or it has been proved to be, an NP hard problem. So what can you do? So for that, I'll give you some idea, and this this kind of techniques we will also use later on. It's a fairly intuitive thing. So given a simple polygon, any arbitrary simple polygon, algorithmically how do we even find out where to place the guards? Right? How do you find out? So what I'm saying is that even brute force, how do you solve that problem? How would you solve the problem in brute force? If I want the minimum number of guards. Again, the problem here is that it is not a discrete problem. Okay, so whenever we talk about NP hard problems in the context of graphs or some permutations and things like that, those are discrete problems, and you know that well. I don't have a polynomial time algorithm, but at least I have some n factorial algorithm or 2 to the power n algorithm or something like that. Satisfiability has 2 to the power n solution because I can enumerate all the solutions. Okay. So here again, because we are dealing with a continuous space, where do we actually place these guards? Okay, to find the minimum.
You can define regions that are not intersecting, and then you have to place at least 1 guard in each of these regions. So that will give us some sort of a lower bound.
Right. Okay. Yeah. So yeah, you are on the right track. So here is, I guess, let me translate what she meant. So I have some arbitrary simple polygon. Okay. One thing I can certainly do is I can think about if this region has to be visible, I need a guard in this cone somewhere, right. Similarly, for this one, if I place a guard, I need to place a guard for this point to be visible in this cone. So if I place something in this intersection, then these 2 cones will be visible, right. So you can
no, but you cannot put anything in that cone, right? I mean, because for example, you cannot put a guard anywhere in that cone, so that
no. So you have to also respect the boundary of the polygon.
Yeah,
you have to respect the boundary of the polygon also. So, but you can define these cones along with the boundary of the polygons, okay, in a way such that you can argue that you can find out all you can essentially enumerate all the feasible solutions. Okay. How do you enumerate all the feasible solutions? One way is to basically take all the possible cones, okay, look at the intersection of all the cones. Now, when you look at the intersection of the cones, okay, so it would look, let us say, something like this. Okay, it is a partition of the plane. Okay, so it will look something like this, and the claim is that any face of this partition, okay, the visibility information is fixed, okay, that whatever is visible from this point is also visible from this point, because you are not crossing any cone boundaries. If you do not cross any cone boundaries, your visibility information. So, these are in some sense some kind of equivalence regions. Okay. Now, moment you reduce a problem to this, then it becomes a covering problem. So, I need to find out. So, for I can actually enumerate for every face which parts of the polygon is visible. Okay. Then I want to find a minimum cover of that. Right. So, this you can straight away sort of reduce it to a use one of your favorite covering problem solutions algorithms. If you use a greedy solution. So, then you can essentially what I am saying, you can get some kind of an approximation algorithm, and the greedy solution itself will give you something like a log n approximation. This is for people who are somewhat familiar with approximation algorithms. Okay. So, the problem essentially is reduced to the following, that I have some sets, I have some elements. The elements are basically the regions in the polygon that I want to cover, okay, and I want to choose some sets which are basically these faces, such that the union of those sets cover all possible elements. So, that is how I have discretized the problem, and then you can solve it. Right. Okay, so, I will stop here today.